Okay, and we are live. Bill, welcome. Floor is yours.
Yeah, you guys can hear me
Yeah, can hear
and you
you.
can see yourselves.
Yes.
Okay, so I was thinking, uh, like to get the basic understanding of class AB amplifiers, maybe we go through the question he sent us first, and then we go in order, in some sort of order called of the problems in Inkwell, yeah? Yeah, I think that's a good idea. And then also,
Yes.
I was thinking about the, what's it called? The Class C amplifier. Yeah, that one. Yeah, that one. Yeah, that one. I haven't seen so many questions and I've also not understood it fully. So we'll do Class A, B now. And then I'm to be presenting with Kamara, but she has a family thing. I'm to be presenting with Kamara, but she has a family thing. So when she comes, she'll take over. But for now, I'm going to do the presenting. Yeah. Okay. So let's get started with this one. No, this one. Yeah. Uh, so this is basically how the class AB amplifier usually looks like. There are two transistors here and a diode here. These diodes here are for biasing. Okay, so first maybe I'll go through the operation of this, what's it called? Class AB amplifier. So when our signal looks something like this, yeah, for all, yeah, it looks something like this. So let's say for the, no, not let's say, it's actually what happens is during the first half cycle, what will happen is this one here is going to be on. This one here is going to be on. So conduction will be taking place and current will in fact come like this. Why will it be on? Because during the first half cycle, we are having positive values here coming in like this. Yeah. So the VBE here is going to be greater than 0.7. Yeah. That means that this is going to be conducting, which means our current is going to flow like this. And what about this one? This here is what we call Npn transistor. And this one here is PNP. So when our input is 0.7, this one here is going to be off because this one here requires it to be negative 0.7 in order for it to do the conducting. So during the second cycle, is it called second cycle? The second half of the cycle, this one, during the first half, sorry, of the cycle, this one is off and this one is conducting. So our current comes like this. Yeah. Notice that here we are drawing current from here. This IC, we are drawing it from the source. But then during the second half of the current, this transistor here goes off, yeah, while this transistor here goes on into conducting. So what happens? We don't draw current. No, what happens is because of this capacitor, during the first cycle, this capacitor was charging by default because there is this thing here, this thingamajig. This uh, during the first cycle it was, what's it called, it was conducting and this capacitor was charging, but then during the second cycle this capacitor begins to discharge, so we come like this. Yeah, it's going to draw current from here like this, and that's how we get to a negative cycle. Notice that during the first cycle, we were drawing from the source, from VCC. Yeah, it was coming. Wait, is there any question? Oh, no, no question. Oh, sorry. Yeah, notice that during the first cycle, we were drawing from the source. That was power we were inputting into our amplifier. But then during the second cycle, we're not drawing from the source anymore. It's coming from down. It's coming from down going up. This will explain some part that's coming up shortly. Yeah, I'm prepared for that part. It's okay. Anyway, so the question is usually to determine the efficiency of this amplifier, this class AB amplifier. The power input is the current drawn from here plus the current drawn from here because of, yeah, the current drawn from here plus the current drawn from here times the voltage, the tension it's at, which is from here to here, which is VCC. So it's VCC times ACC. Let's call this current here ACC. ACC is dividing itself into I1 and I2. Yeah, I think this is what we call I2. Is it? No, let's call it IC. Because for consistency with our notes, or I average. I average is what we call it in our notes, sorry. IAVE. Yeah. I1 is what we call the biasing current, and I average is the current going to the amplifier, the current that actually does the work. Okay, so let's clear some of these things. Oops, sorry. Yeah, let's clear this. Yeah, so that we can do our working. Okay, so during the I bias is simply the current that was flowing here. And how do you get it? There is some voltage, yeah, there is some VCC, and then there is the resistors. But it's not going to be just VCC divided by the resistor 1 plus resistor 2 because of these two diodes. We have to consider these two diodes in our calculation of I1. So the formula is I bias is equal to VCC minus 2 VBE. Obviously 2 because there are two diodes here. 2V over 2R1. It's actually supposed to be R1 plus R2, but a lot of the times it tells us that R1 is equal to R2. So this is just going to be our formula for I bias. This is how we get the biasing current. The next aspect of this question is to get the, what's it called? The current, the I average, this one, I average, the current flowing through the transistors. How do I get rid of this? Sorry about this checked part. I'm not sure to get rid of it. Should have thought about that earlier. Anyway, let's just keep going instead of wasting time thinking about it. So I average the current flowing through the transistors, like down like this. Yeah, the one which comes like this in the first half cycle, and then comes like, yeah, the current that comes like this, because that's the current we're considering. We don't need to consider the current during the second half of the cycle. Why is that? Because that current doesn't come from the source. We're not drawing it from the source. We're not inputting it into the system from the source. That current is the current that was saved in the capacitor when during the forward cycle. So we already account for it during the forward cycle. We don't need to account for it again during the reverse, during the negative cycle. Yeah, and the formula for this current is VCE over, VCE over 2RL. VCE over RL, sorry. It's VCE over RL, but then I will get to that. It's VCE over RL, the current coming here. Why? Because we are not considering the VCQ, because like you know that this transistor is just a drop, so we do not need to, like we do not need to, how do I say this? Yeah, this transistor just gives us a voltage drop, so we do not need to count it twice again. Like, I hope you're understanding what I'm talking about. Or, yeah, I think it's better to start from the AC load line. Let me check. AC load. This is AC is equal to, this is the formula for the AC load line, sorry. I C is equal to ICQ plus VCEQ over RC minus VCE over RC. This is the formula that Celestine derived on Wednesday. This is the AC load line. And then for this, the equation for the AC load line. But then, if you look at it, if you look at our, sorry, how do I get this? Let's just look at this one. If you look at our diagram, the total, this VCC is being is dropping between these two transistors in DC, in the DC load line, in the DC parameters, because this will become an open circuit. So this VCC is being dropped by these two transistors. And because they are identical, we'll say that VCE has to be half of VCC, because half of the voltage drops in the first transistor, then the other half drops in the second transistor. Like there's no other way of, there's nowhere else the voltage can go through in the DC side. That's why, so we end up getting that VCC is equal to VCE Q is equal to VCC over 2. Why? Because there's nowhere else that the current can drop. Like voltage, there's nowhere else that the voltage can drop. Like there's no other resistor here or here or here. So all the voltage has to drop within these two transistors. Because they're identical, half the voltage drops there and half the voltage drops there. I hope that's clear. So that's why VCEQ is equal to VCC over 2. And then the next part for this AC load line is to realize, yeah?
Just to add on to that explanation as to why VC EQ is half of VCC.
Yeah.
I'm not sure if helps or makes sense. Okay, I didn't quite understand it myself, but I read somewhere that the reason as to why the VCQ is half of VCC is because in the biasing circuit, the biasing resistors and the diodes are equal, they're the same.
Yeah, the resistors here, where? Oh, here. So this.
The D's.
Yeah, the D's are equal, and then also the R's are equal.
Yeah.
Yeah, that
So,
makes perfect sense. Because half of the Nini is here, and then the other half is here. So it also has, I think it also explains the same thing. Yeah, thank you for that.
You're welcome.
Okay. So the next thing we realize is from this equation that we realize that VCQ is independent of ICQ. VCQ is independent of the current flowing through because of what I've said. I've said that VCQ has to be half. There is no other option for VCQ. It has to be half the VCC. So that means that it's independent of ICQ. Yeah. So some questions from which comes to help us in this AC load line equation. One, we know that VCQ is independent of ICQ. So ICQ can take values, any value between 0 and infinity, and it will still work. The VCQ will remain the same. Yeah. So if we do not bias, if like nothing else is running, then ICQ is going to be 0. Yeah, if we bias it, it goes to infinity. That's as per the notes we've written. The next thing is that, so what we're left with is VCQ, IC is equal to VCQ over RC minus VCE over RC. Yeah, but VCQ is VCC over 2. So we end up getting IC is equal to VCC over 2RC minus VCE over RC, where RC ends up becoming RL because it's the load resistance. Yeah. So when we come back to our this one, we have shown we know how to get the biasing current. So the next one to get is the average current. In order to get it, we need to first get the saturating current. And the saturating current is on that graph. Okay, let's draw the load line first. Clear. Okay, our load line. How will it be? Yeah. We start with the DC load line. You come to this point here, VCC over 2. Yeah, VCC over 2, and then it's our vertical line. And you know why it's vertical? Because VCE, sorry, let me give the axis first. Here, the horizontal axis is VCE, VC, and then the vertical axis is IC, the collector current. So VCE, the DC load line is just a vertical line because the VCE is independent of IC. And then the AC load line, we come to this AC equation. It's telling us that VCE, this VCQ minus VCE. So, and we have VCQ is VCC over 2. To get the to get another point, so we know that our uh, sorry, you know that it has to pass through this point here, but then we want to get another point. The next point, oops, the next point that we can get is if we set VCE to 0, because setting VCE to 0 gives us a point on the IC axis. So if we set VCE to 0, we're going to get that IC is VCC over RC over 2R, VCC over 2RC, 2RC or RL, the load resistance. So that gives us a point here. And then you just connect the two lines. And this is the AC load line. Now this point here, VCC over 2RL over this point here is what we call the saturation current. Yeah, this is what we call the saturation current. So if we come back here, VCE over 2RL gives us the saturation current. And therefore now we have a way of getting the IC sat, because the saturation current we've been told is just VCC over 2RL. Now, the next part is getting the, what's it called? The average current, because the average current is the one which we said comes like this. How do we get it? Average current is just IC sat over pi. There is a long derivation in the notes, you can go over it. It's just integrating and doing some stuff. This here gives us I average. Yeah, so this is how we get the two currents, the I1 biasing current and the average current. The biasing current is this. These are the two equations you just need to keep. Like, they help a lot if you know them offhand. Yeah. So now we can get the input power, because if we have VCC and we have the current being drawn from the source, then we just multiply the two and we have input power. The next thing is the output power. Output power, we come to our graph. Where is it? Yeah, output power, you need to think of how our is going to be, our output curve is going to be drawing, looking like moving, shaped. Yeah, it's so for this kind A class AB amplifier, because we have NPN and PNP, our output voltage comes like that. Yeah, and our output current comes like that, because there's positive and there's a PNP and there's an NPN. Yeah, so our peak value of output, our peak value of output current is the same as our saturation current, and our peak value of output voltage is the same as VCE. Yeah, because peak is just from the center line to the maximum. And peak here, also here from center line to maximum. Okay, so that's basically how you solve all the problems regarding these class AB amplifiers. But I know we're going to come to specific ones with some specific numbers. But like, this is the trend. This is how you solve it. Steps, maybe if you want to write steps. Step 1, get biasing current. How do you get biasing current? It's VCC divided by minus VCC minus VBE, 2 VBE divided by R1 plus R2, always like that, because these two resistors and these two diodes divide the total voltage that's crossing here. So it has to be that, it just has to be VCC minus 2 VBE divided by R1 plus R2. Step 2, get the current. Get the average current. How do you get average current? You first get saturating IC sat. How do you get AC sat? AC sat is VCC divided by 2RL.
Yeah.
So VC, what am I saying? So how do you get the average, the saturation current? It is IC. How do you get the saturation current? It is VCE divided by RL. But VCE, remember, is equal to VCC over 2. So the second step is do VCC over 2RL to get the saturating current. And then once you have the saturating current, you divide it by pi to get the average current. That's how you do the, what's it called? The saturating and average current for, that's the next step in this. Then the step after that is you multiply the two to get input power. Yeah, and once you've multiplied the two to get input power, you can look for output power. What is the output power? Output power is output voltage times output current. And output current is the same as the saturating current you had already gotten before. Output voltage is VCE, which is just VCC over 2. And then you divide the two to get efficiency. Okay, now let's start some exam questions because usually reverses the process sometimes. Let's start with this one, I think. The first one, explain briefly using a sketch the cause of this. This is in the notes. Ahmed, does anybody want me to go through it? Does anybody want me to go through these explanations? Using a sketch diagram, the cause of crossover distortion. How to yeah.
What year? This paper is from what year?
2015. This is yeah, 2015, 2016. You can open it. Okay, let me just say them because I think I've been asking. I could have explained in the time I used to ask. Using a diagram. Yeah, I'm not drawing. But the, okay, let me just draw. For the regular class, AB doesn't have those two biasing resistors. So crossover distortion is this. You see here, there's some signal that has been clipped away. It's gone somewhere. And why does it occur? Because there's no biasing. So we need the signal to first go over 0.7 before we can start conducting. So here what happened was the signal was actually below 0.7. Like the signal was 0.5, the transistors were off. So some of the clipping occurred. The next one was how the design of class AB eliminates. The design of class AB eliminates because there's biasing resistors. Yeah. So the biasing resistors ensure that the transistors are on for values below the 0.7. So that's why the class AB solves that problem. This one, maximum efficiency is that, DC power consumption is that, VCC is that. Sketch the DC, determine the values of R, L, and R. Oh my, R1. Yeah. Is there anything? Oh yeah, and they've told us that R1 is equal to R2. So this is R1. Then if you see R2, this happens to be R1 and then RL. We follow the process exactly as it is, except now we put X's. You'll see what I'm talking about. We said that step 1 One is get biasing current. How do we get biasing current? I bias. I bias. I bias is equal to VCC minus 2 VBE over 2 R1. Yeah? Yeah. Over 2 R1. And our VCC we've been given is 15 volts. Good night. VCC we've been given is 15 volts. So I bias is equals to 15 volts minus 2 VBE is 1.4 because of first semester divided by 2 R1. But what is the value of R1? Question mark. We don't know. We're looking for that. Have they given us more information? They've told us that DC power consumption is that. Okay, that's the next thing we're going to use. Sorry. The next thing to do, step 2, is get average. Average. Yeah, and how do we get I average? I average has step 2.1. Yeah, step 2.1 is to get IC saturation. And how do we get AC saturation? AC saturation, whereby IC saturation is equals to VCC divided by 2RL. Yeah, this is the formula because of the derivation we went through. A VCC divided by 2RL gives us AC saturation. Yeah, and then once you've got an AC saturation, step 2.2, you divide AC saturation by pi. I average is equals to IC sat over pi, which is equal to VCC over 2 pi RL. 2 pi RL. I average is IC sat divided by pi. Yeah, this is the equation for I average. Okay. Now, step 3 would be to get total DC current. But we already know that the total DC current we've been given was 379 milliwatts. So we just substitute it into that equation. So here we have 379 milliwatts is equal to the first one, which was VCC, which is 15. Our VCC is 15 volts. 15, because the total DC current, remember, is the biasing current plus the average current. From the diagram, the biasing current is the one that comes like this, and the average current is the one that comes like this. So it's going to be 15. 15 over 2 pi RL plus that's 13.6 over 2 R1. R1. Okay, and these are two equations. This is the first equation, sorry. This is call this equation 1. But it should be clear that we are going to have two equations because they're asking us to find two things. So we should know that this is going to end up being simultaneous equations, something up there in your head. Okay, so once you have the DC current, now the next step is usually get step 4, sorry. Step 4, get input power, which is equal to IC, IDC, the DC current. This is the input power, DC current times VCC. But in case you're not getting why it's VCC because this DC current is flowing in this system. So it's flowing in a system with a voltage of VCC. That's why we have to multiply it with VCC. If you remember in the previous topic, what was it called? The topic for these direct coupled amplifiers, to get the total power, we were doing the total current in times the total voltage. That's why we have to multiply by VCC. So this would be equal to IDC. The DC current, we had it already, 379 times VCC, which is 15 volts. Sorry, 379 milliamps times 15 volts. Okay, so step 5. Step 5 is usually to get the output power. Get out. And what's this output power? Output power is we're looking for the maximum output power so that we can get the efficiency. Yeah? Yeah, we're looking for the max. I don't know how to explain that differently. We're looking for the maximum output power. And if you can recall from this graph, maximum output power, okay, we know that the formula for VRMS times IRMS. So if we are looking for maximum output power, it's going to be VRMS, which is V peak divided by root 2 times IRMS, which is IC sat divided by root 2. So VRMS times IRMS, that gives us the maximum output power. Interesting. Where am I? I think I'm here. So get output power, which is equal to VRMS times IRMS. Okay, and how do we get this VRMS times IRMS? VRMS is, we've seen already, it's just VCE over root 2. And see the square root side, root 2. VRMS times IRMS. IRMS is IC sat over root 2. VRMS times IRMS over root 2. VRMS times IRMS, put real values to this. VCE, recall from the beginning. VCE is VCC over 2. If you don't remember anything, over 2. So over 2 root 2 times IC sat, and IC sat, we've gotten it right here. IC sat is VCC over 2 RL.
Bill,
Output power, yeah. VCC, I recall from the question, VCC was 15 volts, yeah. So here we're going to have 15 squared, 225 over, sorry, this is AC sat over root 2, so 2RL times root. Sorry, I hope it makes sense why I'm adding this root 2, because AC sat is one which is VCC, AC sat is VCC over 2RL, and now I divide it by root 2 because power is AC sat over root 2. I think that makes sense. So over root 2 times IC sat. IC sat is this here, 15 over 2RL, 2 root 2 times RL. Okay, I'm going to push those root 2's and 2's outside so that we're left with RL. And then here, instead of having root 2, and 2, I just have 4. Hope you see where I get the 4. Root 2 times root 2 times 2. That's root 2 times root 2 times 2. That gives us 4 times 2. Actually, it's 8. I'm sorry. It was not too clear. I hope it's 8. 2 root 2. Let's just put it in a calculator. 2 root 2 times 2 root 2. 8. Yeah, we are actually correct. So this is going to be 15 over RL. Yeah. Now you can see the two equations I was telling you guys about. This one here and this one here. But we haven't finally got the second one because this one here is just output power. Yeah. Now we don't have the final output power, but what we do have, yes.
A question has been raised concerning step 3.
Yeah. Yeah.
Concerning step 3, where is the current coming in?
Step 3, get total DC current.
Because
Which where you're asking?
you're doing I
Yeah,
bias
I'm doing a bias plus I average. Yeah. Wait, I think I should get your question better. In step 3, where is total DC current in the equation? To that step. So we have total DC is equal to I bias plus I average. And then we've been told from the question that, sorry, this is DC power consumption. Sorry, not the DC current. So this gives us total, sorry, I did not see. This is total DC. This gives us total DC current, yeah? And then the total output power is equal to this 15. The total output power is the DC current times the voltage. I'm so sorry. This is the total input. Sorry. Yeah, the total input power is the DC current times the voltage, which is this. I'm so sorry, I did the wrong equation. The DC current times the voltage. This gives us the total, this gives us the total input power. Yeah, the DC current times the voltage, which is this. And then the total output power, the total power consumption is the power consumed by the system, is both the output power and the nini. So yeah, I'm sorry, I've found where I went wrong. This is what is equal to 379 milliwatts. So sorry, I gave you the wrong value here. This is what's equal to 379 in milliwatts. Total power consumed, which is the power we input. And then the total output power is this monster thing. Yeah, 225 over times 50 over 8 times RL, yeah? And then next is to get the efficiency. Sorry, so sorry. Get efficiency. And the efficiency is the output power divided by the input power times 100. And we've been given that that efficiency is 74.3. So 74.3, let's give the equation now, please, is equal to 1. So is equals to 74.3 is equals to equation 1 over the input power, which is 379 times 100. Yeah. Maybe we can do some simplifications at the beginning stage, like somewhere here, or maybe we can do the simplifications here, whichever you want. But I think maybe this one here is doing the simplifications here is a bit better, so that we only have RL in our final equation. So we can write R1 in terms of RL, or just need to check whether I haven't done anything else wrong. Okay, yeah. So in fact, I think it might be easier to just do it this way. We get RA first and then we substitute RA into this equation. Yeah, I think that will be easier. So how do we get RA? Here we have 74.3, 0.743 is equals to 0.743 is equals to equation 1 over 379. So is equals to times 379 is equals to equation 1. Yeah, 0.743. I hope you can see what I've done. I've just taken this 100, it was times 100, so I've divided by 100 and then over 379, it has come up here, is equals to equation 1. And what was equation 1 is this. is equals to this. Yeah. So now we can get the value of Ri. How? First of all, we multiply. So here we're going to have times 8 over 225. And then we're left with 15 over Ri. And then now we can get the value of Ri. Okay, let me punch it into the calc 1 second. So RL, I found it to be, wait, what value is it? Yeah, I found R, sorry about that. So I found RL is equal to 9.6 ohms. Yeah. Then now the next part is to find R1. So you take the value of RL from here and put it into this equation. Yeah.
In equation 1,
Question.
5. Yeah. What
Yeah.
Elizabeth has said.
In equation 1, I don't get why we are multiplying. Why we are multiplying by 15 in equation 1. It's equation 1 is 225 over 8 times 15 over Ri. Yeah? Wait, you don't get why we are multiplying by 15. 15 was the voltage.
You know, it's because you've already done 50. You've already done VCC times VCC to get to 20.
VCC times. Oh, so this isn't supposed to be there. So the 15, thank you for the correction. Here it's supposed to be 1 over RL. 25 over 8 times 1 over RL. 0.743, that. Is everything fine now? Two root 2 times 2 root
Yes, I
2,
think so.
8, 1 RL to 25 all over 8 times 1 over RL to 25 over 8 times RL. 25 over 8 times RL. Then we come here 0.743 times 379 times 8 over 25 is going to give us 1 over RL. So RL becomes a very small value. 0.641. No, something seems to be off. Wait a second. VCE, VCC over 2. AC set, which is VCC over 2 RL root 2 output power equation 1. Output power over input power times 100. That's not happening. Can anybody see what I've done wrong? 0.6 for now. It's never that small. Oh, sorry, it's 10.01. Are you getting 10.01 as well? Am I doing my own things again? Oh God, what have I done wrong now? The 13.6 in equation 1. Equation 1. There's a 13.6. Or in this. Or this. 15 over 2 pi plus 13.6 over 2 Oh, the 13.6 is VCC minus 2 VBE, which is actually wrong because VCC is 15 volts. Oh yeah, it's correct. VCC minus 2 VBE. That's where the 13.6 comes from. The 13.6 is VCC over 2 minus 2 VBE. And then that you divide by 2R1 because you divide by 2R1 because it's the biasing current. And then this first part here is the, what's it called? The I average, the average current. The input power is 379 milliwatts. Hope that answers the question. Crap. Hmm? RL is supposed to be about 10 ohms. I'm getting 10 ohms, but I'm feeling like I've forgotten something. 225 over 8 RL over 2 root to 8 RL. This is squared over 8 RL. That divided by 379. 379 goes there, divided by 100. 8 by 225. I think we might be right. 10.01. Or is something missing? I hope we are right. 10.0123. Looks right. It feels right. I hope we are right. Unless we've forgotten something important. Please tell me if we've forgotten something. Anyway, now that you have RL, you come here to this equation. Put RL here. So you're going to have R1. No, let's leave this term. 379 minus no, wait, okay, let's just come here. 379 minus 15 divided by 2 pi RL, where RL is that 10.01, is equals to 13.6 times 15 over 2R1, 13.6 times 15 over 2R1. Yeah, then you make R1 the subject any way you want. Okay, let's work with watts. 0.370. Oh, that's what I had missed here. Supposed to be 0.379. 0.379. 99.87. 0.743. Okay, 3 times 0.379 to change this milliwatts to watts times 8, because we are bringing this 8 to the other side, divided by 225 is equals to 1 over RL. Yeah. So to get RL, do the reciprocal of that, which is coming to 99.8788 ohms. And then now you put that value of RL here, 99.88. Yeah, and then you solve for R1. R1 is usually in the order of kilo ohms. So let's solve. Yeah, it's coming to 287 ohms. Yeah, so those are the values you've gotten. I really hope I haven't forgotten anything. Please tell me if I've forgotten. Your input is highly appreciated. I really hope I haven't forgotten anything. Yeah, thank you. So that's how you do this first question, how you get the values of RL and R1. And I've shown you how to sketch the DC load line. Any questions? Please, questions? Questions will help a lot. No, okay, if you, I remember a question I had when I was revising this. If you remember in the AC, in the class A amplifier, yeah, when we were calculating the current, we said it's ICEQ. Wait a minute. Yeah, it's ICQ plus VCEQ minus VCE over RC. That was the equation for our load line. Yeah, the load line equation we have here. ICQ, with the one which had ICQ. So now the question is, why, how comes for this one, we considered the ICQ just the way it is, but then here in the class AB amplifier, we aren't considering ICQ, yeah? Yet we've said that ICQ can take any value. Why is it that we are considering it then, but we aren't considering it now? I hope mnanisikia.
Bill,
Yes.
I think you're asking like why in class AB, like we don't consider any value of IC.
Yeah, we don't consider the no, we don't. We do. We am asking why you don't consider ICQ. The quiescent.
Like in the
See in the AC one.
see like
Yeah.
okay. See, okay, do you have that diagram of your of your load lines.
Yes. Yeah. The DC one is this one.
Okay. Even when you drew, even when you draw the equivalent, like the DC equivalent
Yeah.
of the class AB,
Yeah.
you'll notice that IC is either 0 or infinity, as you said.
Yeah.
In your because when you look at the diagram, there are no resistors
Yeah.
on that branch where we have the transistors, and
Yeah.
so
Yeah.
because of that, I don't think IC can be any value. Okay, maybe, but will literally be a value because there will be no drops, no voltage drop. So let's say it's biased, IC will
Huh?
be infinity.
Yeah.
And if it's not infinity, it's going to be 0.
Correct.
So I think that's why it's not considered. Because if you consider infinity, like you'll get IC sat as infinity.
Yeah,
So
but
I
they've
guess
said
that's why
that
you
it
just
will
use
be
0.
infinity.
Pardon?
They've said that it will be infinity. So why aren't we considering that
Yeah,
infinity?
so then IC sat will be infinity. If you input it in your equation, I think IC sat will be infinity.
Yeah, and then it will lead to some issues. But related to that,
Yeah.
I think there is some deeper understanding that comes along if you keep thinking in that path. So related to that, in the class A amplifier, we were thinking about, we weren't considering this, the I average. In the class A amplifier, we don't consider I average. Why is that? Yet in the class AB, we are considering I average. Anybody? In class A, in class AB, we consider I average, but in class A, we don't consider I average. Like ICE, we were considering it in class A, but then IC plane, we aren't considering it now. I average, we are considering it now, but I average, we weren't considering it in I. Like we didn't do the integration thing and the, like, why are we swapping the two is the next question. Not that what Kamara said is wrong, it's actually completely correct. Because like whatever value of AC we consider, it either completely ruins our results, because here in the part for getting the efficiency, we're going to have infinite power. Infinity power is our input, is infinity power. So it's going to be a 0% efficient amplifier. Yeah, 0 to infinity. Yeah, it's going to be a 0% efficient amplifier. And if we consider 0, it doesn't have an effect. We get the values we've been getting. So now the question is, why are we swapping the two? Like, why don't we, like, is it just a matter of convenience or? Okay, so I shall answer my own question. My answer is that I claim that we actually do consider both of them in both cases. In fact, I'm saying that it's the same thing. Like IC SAT is this, ICE is actually an average. That's what I claim to say. Why do I make such, how do I make such an absurd claim? They're definitely not the same. Because if you think about your thing, yeah, your load lines, yeah, you're considering your load lines and your load line equations, yeah, you're thinking about those things in that kind of aspect. You are, for your class amplifier, you're going to have something like this. So offside. Okay, I hope you understand me and my challenges. For your class A amplifier, you're going to have something like this, yeah? And then your output curve is going to be of this form, where this part here is equal to this part here, and here we are calling it ICEQ. Yeah? is going to be this kind of thing. So now, actually, if you take an average of this thing, you're going to find that the average actually ends up being ICQ. So it's actually the same thing. Like for the class A amplifier, we do consider it, it's just that it happens that that value is exactly the same as the ICE value we already obtained in the previous step. Okay, so let's maybe look at one more question. This one, wait, have you understood that reasoning?
Wait, Bill,
Yeah.
I have a contribution, but it's more of like a question because I'm
Yeah.
not sure about it.
Yeah.
Can we say that the reason why we use ICQ in the class A amplifier but use I average in this one?
Yeah.
Because when we're considering ICQ in the class A amplifier, it's because we're using an IC, a collector current value that comes from, quote unquote, comes from the DC source. Because when we want to find ICQ, it's a DC current, so we draw the DC equivalent to solve for it. But when we're using the I average for an AB, a class AB amplifier, it's because we're taking the average current that is the average collector current that is produced, induced, whatever, by the input signal, which is AC.
Yeah, that is making sense. But the question that arises from that is that in this graph, you do know that, like, it will vary. It won't be constant. Yeah, it won't be constant at any given value. It's going to vary like this. Like, it will keep varying. So you can't say that the power being drawn from the source, you can't say that the power being drawn from the source is a constant value, because as the in the class A we only have one resistor. Okay, so let's think like that. Because in the, what's it called, in the class A, this this important thing, what is this thing? In the class A, this amplifier, this transistor actually does make the current that is flowing fluctuate. Like it's not that, like, what I'm trying to say is that it's not that in class A, B, that in class A the current is always constant, because you know that it's an AC current being amplified. And that AC current, for it to be amplified, is the DC value that provides us that swing, that capability to swing. Yeah, it's the DC value. So it's the current that's being drawn from here that keeps on varying to give us different values of I something, different values of something important, different values of IC. Yeah, but and that's the same thing that's happening here. Yeah, it just happens that for the class A amplifier, it's the ICQ current is actually equal to the average of the current that will be drawn from the source. I hope I'm making sense in a way.
Yeah, you are.
Okay. Okay, Daniel, I said you was getting different answers. It's important to have variety. Yes.
Bill,
Yes.
I have another question.
Yes.
In what cases do we consider ICQ to be equal to 0?
In what cases do we consider
ICQ equal to 0.
ACQ to be 0? Okay, as per the notes, like you can see that here, there is no resistor here. So that's the argument that is taking place. Like we know that there is voltage being dropped here, but there is no resistor here. So the question is, what current is going to be drawn from here? You know that that current is independent of the voltage across here is independent of the current that's flowing here. So that if we don't bias this transistor, then the current being that will be drawn will be equal to, what's it called? Will be equal to 0. But if we do bias it, then the current drawn will be infinity. Because if you put any value of current, you're going to have the same value of VCE. Why is that? Because the value of VCE is independent of the current being drawn. But you can't just, like, the question would be, why do we have a current of 5 here instead of having a current of 13 or 12 or whatever? Why do we have some other current instead of some other current? And that's why we say that if you bias it, the current flowing through it will be infinity. If you don't bias it, the current is 0. Yeah, that's it. I hope it's making sense.
Yeah, yes, it is.
Okay. Daniel and Elizabeth got the same answers. Could you tell me where I went wrong, or oh, everybody has different answers. Wow. We'll come back to it, but that's the procedure. Okay, let's do some other question, because, like, I hope we are understanding the procedure. The procedure is the same for all of them. It's just the numbers that I might have misplaced somewhere. But we'll get, I'll do them correctly. I'll ask Celestine to do them for me correctly and then take a picture and send to the group. This one, we've been given R1 and R2 and RL. You see that in the kilo ohms, and this one is small. Sketch the C in DC, it's the same as the previous one. Let's not go through it. Maximum efficiency. Wait, is this the one we've done? No. The maximum efficiency of the amplifier is that. Determining the supply, power supply in VCC. And this one is going to give us some quadratic that's going to be a bit ugly. But let's get to it. The steps remain the same. Step 1, get the biasing current. Step 1, get the biasing current. Wait, sorry, you need to read the, which is VCC minus 2 VBE. So here, instead of having this 15, we have VCC minus 1.4 over 2R1. And R1 is equals to R2. So 2R1 works. If R1 is not equal to R2, you can't do 2R1. You have to do over R1 plus R2. So over 4.65 times 2 over 9.3. 9.3. Yeah. And then step 2, get the I average, which starts off by getting IC sat. So here it's going to be over 20 because the RL is 10. That gives us IC sat. The next step is to get I average, which is just that divided by pi. So over 20 pi. So we're going to have VCC over 20 pi. Yeah. 62.831 something. 52.8319. 62, sorry. Step 3, get total DC something something, DC current. So the total DC current is the bias current plus the average current. The bias current is this. So we have, oh sorry, remove this. Control V, Control Z, Control V, that one, plus the bias current plus the average current, which is this. And that's our step 3. The next step is to get the input power, which is the DC this total DC current times VCC. Now you are saying it's an ugly quadratic. So it's just this times VCC, Control C, Control V, and that, yeah, we don't need the rest of this. And this gives us the total input power. See, if you have the steps, it hopefully flows quickly. Yeah, yeah, I hope it does. Not backfire. Yes. Bad manners. Next one, get the output power, which is the VRMS power for the output, VCE over root 2, which is VCC over 2 root 2, times VCC over RL. We have it as 20 times root 2. So IC sat. Yeah, which gives us this 2 root 2 times root 2. That gives us 4. 4 times 20, 80. 80. So VCC over 80. Yes, yeah, makes sense. Yeah, looks like we're moving on nicely. And then the efficiency. Now the efficiency is done, which will tie everything together. Because the efficiency is simply the input power times the output power, output power over input power times 100, and we've been told efficiency is 78.1. The efficiency is 0.781, yeah, is equals to the output power, which is VCC over 80. So it's going to have VCC over the denominator is going to be something very big and ugly. But the good thing is this VCC is going to be in the denominator. So it will cancel with this VCC. So we have 1 over 80 times that. 80 times the ugly thing, this one here. And then now you solve for VCC to get your, what's it called? Your answer. So maybe we can try to solve for VCC. But first, let's make it look neat. Let's make it look neat from up here. VCC. Maybe we can write it with the same denominator. Or do you think it's okay? Just continue with it looking bad. Now let's make it look good. The denominator is going to be 1 over plus 1 over 0.12 as a fraction. 1 over 8.1. Oh, sorry, let me just do that. Okay. Here we done. Here we do times 80. And then our denominator is going to be that, so we can reciprocate it. We get something like 84.337 over some fraction 72.131 VCC minus 82.9634. Yeah, hope we're getting the same thing. Please, please, please. At Bill, are most of these questions related to what you're doing? Mostly quadratic. Yeah, I thought it would end up being some quadratic equation because of these two VCCs, but fortunately for us, they cancelled with this VCC. And then, so we are fortunate there, I guess. And then you cross multiply and get the value of VCC. Has anybody done it? What have we gotten as VCC? Nobody's doing them. Am I talking to myself? I'm talking to myself. Okay.
You aren't.
Oh, thank you, thank you. So do the cross multiply.
No, you're not talking to yourself.
Thank you, Andrew. You see, I knew it's Andrew even without coming to check. IQ. So you cross multiply and then you solve for VCC. Wait, Chabet did this question. This question. Why am I disturbing myself? See, Chabet, you tell me what you got.
I didn't do this question, Bill.
What? So I have to finish. Okay. Has anybody gotten an answer? Has anybody gotten an answer? Oh, currently I'm doing 2014. Let me post that one. Wait, Celestine has a question on the dad. What's your question, Celestine? Celestine. Is Celestine around? Oh. Yeah. 49 volts. That's a big value. Variety is the spice of life. Yeah, maybe. Didn't tell me this to be a K there, sorry. Okay. Is anybody getting anything? Yeah, I'm also getting such small values. But there's something wrong. You must have forgotten something. Oh my God, what a disaster. I knew it. VCC over 2 root 2 times VCC over 20. VCC squared over 80. And then when VCC cancels, so we have to just bring VCC squared over 80, because there are 2 here. And then the next one is to come here. And then it one is equals to this big thing times VCC. So the quadratic does come. And then we can't just do that. So that due to time, is equals to VCC. Okay, let's give something more reasonable. Okay, from this I'm getting something like VCC is equals to 8.2 something. Wait, let me just finish it. Yeah, I'm getting VCC 7.95 in equation 5, VCC over 80 and VCC squared over 80. Yeah, you are right. It's supposed to be here. VCC squared over 80. And then the VCC squared over 80, now one VCC will cancel with this VCC because we're going to have this over this over this. So this VCC cancels with this VCC. And then we're left with VCC over 80 times all of this is equals to, times 100 is equals to 78.1. And then you divide by 100 and bring this 80 to the other side. So we're left with this is equals to the right hand side, this, which if you simplify, I think you get this. So this is what you're going to end up with, because one VCC will cancel out and then you'll be left with this one VCC. Yeah, getting the same thing as Sean. Thank you, Sean. Is anybody else getting something like that? But I hope you're all understanding what's going on. And there are 4 minutes, so I'm going to stop presenting. Is there any question? I'm really sorry I hadn't written down the solutions before. I thought like I wouldn't make so many errors, like transferring the right number and yeah, and forgetting to convert milliwatts to watts. Thought it would be more straightforward. And also, I just finished understand, like I understood how to do the question like at, what's it, 8:30. So that's 33 minutes from now is when I understood how to do the question. So, but I hope you understood how to do these things. I'm sure this is the way. It's just that the values. Any questions? Wow, tough crowd.
We've understood, Bill.
Thank you. Thanks, Bill, for the presentation and for answering of very many questions and for engaging us towards the end. That was nice work, Bill, and from everyone. So don't take too much time. It's 1 minute to 11. The cut is Monday. Good luck, everybody. So what now? Well, today is the last day of this week, which means that next week. First of all, do you guys want to meet? When do you guys want to meet next week? Because I don't think we'd want to do Monday right after an analog cut.
I'm thinking we see how Monday unfolds and then we text in the evening. If we, I don't know,
So we wait for Monday to decide on Monday.
Yeah, wait, but if we decide on Monday, then that means we won't be meeting on Monday.
So what are you saying?
Yeah, what am I saying? From the sound of it, it would appear I'm suggesting we do not meet on Monday.
Nigel said Monday is fine. Elizabeth has suggested Tuesday. Dan wants to meet during the cut.
Yeah, I know. He's been saying it since last week. Okay. Well, I think we should approach it in good faith, have it that everything will go well on Monday, and so we can meet on Monday.
Meet on Monday night.
Yeah, Monday night. So what are we meeting for?
Yeah, what will be the agenda of Monday night?
I am thinking that we take up something light, something like EMF.
But you know, we the last meeting we had, I think the last meeting we had on Friday, not yesterday, the other Friday.
Yeah.
We posed ECT questions to each other.
Oh yeah. But I'm thinking. Oh, you can stop the recording by the.
I keep forgetting.